Here are solutions to homework set number 4 for ECE 111. This homework set looks at using Matlab to solve for n equations and unknowns. That's the type of problem you run into when you take Math 129 linear algebra. We'll also look at doing curve fitting. Given a bunch of data, come up with a line or parabola that passes through the data. Now the first three problems deal with n equations and unknowns. If I have two equations, two unknowns, one way to solve is to use matrices. I'll rewrite these two equations as a matrix. If I take my unknowns x and y and write them in this form, then the first column is times x, second column times y. This equation, 3x plus 6y is 5, becomes 3 times x plus 6 times y is 5. Second equation, 2 times x plus 5 times y is 10. Treated as matrix B, this is y. I could then solve. My answer is inverse of b times y. So trying it, here's my B matrix, start of matrix, 3, 6, next row, 2, 5, end of matrix, Y matrix, inverse of b times y. There's my answer. Two equations, two unknowns. Now Matlab is really good at this type of problem. If I have three equations, three unknowns, same thing. I'll take my unknowns, write them in this form, x, y, z. The first equation is 4 times x plus 1 times y minus 5 times z is 6. Second equation, third equation. Put that into Matlab, solve, there's x, y, z. Three equations, three unknowns. Four equations, four unknowns is also pretty easy. Just take the equations, put it in matrix form, throw that into Matlab. So here's my B matrix, here's my Y matrix, there's B, Y, solve, inverse of b times y, done. So Matlab is really good at solving n equations and unknowns. What that means is that anytime you run into a problem, if I can rewrite it in the form of n equations and unknowns, I can throw it in Matlab and solve. And we do that trick over and over again in electrical computer engineering. You're going to use this trick a lot. Problem 4 onward looks at what happens if I have more equations than unknowns. For example, if I go to the National Oceanic Atmospheric Administration, they've got data measuring global CO2 levels. Now these are located at different spots. They're also available on Bison Academy. Click on right here. Here's my data. This is the year. Here's the CO2 levels. And you can see there is lots and lots of data. Let's do a linear or parabolic curve fit for that data. Now as you can see, I've got more data than unknowns. So to get that data into Matlab, what I'll do is first say data equals, let's do that Matlab, data equals start of matrix, paste, end of matrix. There, I just have a whole bunch of data points in Matlab. The third column is my year. The fourth column, oops, is the CO2 levels. If I plot the two together, somewhere, there's my data. To do a least squares curve fit, I'll set up my basis function. In this case, year squared, year and 1. I want to come up with a parabolic curve fit. Here's my unknowns. It's the inverse of b transpose b transpose times CO2. That's a least squares curve fit. There's your three unknowns, a, b, and c. And plot them together. Year versus CO2 in blue, year versus curve fit in red. Curve fit is just b times a. Voila! There's my parabolic curve fit. If I want to do other curve fits, just change the basis. This is a linear curve fit, year and 1. We calculate a, that's your ax plus b. Plot, I get a straight line. Again, least squares curve fitting is really easy. For parabolic curve fitting, that's what I get for a, b, and c. And if you plot the two together, There's the red line, blue line's the data, red line's the curve fit. Matches pretty well. From the data, if I want to know when do I reach 350 parts per million, 500, 1000, I need to do a trick. There is no function in Matlab for function equals 350. There is a function equals 0. That's the Matlab command roots. So to solve this equation, I'll bring the 350 left. And now it's function equals 0. I can do that. So what is the roots of a minus 0, 0, 350? So that's 0 times y squared, 0 times y, 350. It says I'll hit 350 parts per million in the year 1988. And that kind of makes sense. 350 parts per million right here in the year 1988. That checks out. Now let's predict the future. When do we hit 500 parts per million? That's in the year 2051. 1,000 parts per million. 2157. If nothing changes, that's what I can expect the CO2 levels to be in those years. Least squares curve fitting can be used for other data sets. Just give me data, I can curve fit it. For example, Hector Airport's been recording temperatures in Fargo since 1942. Pull that data into Matlab. And again, you can do that on Bison Academy. Here is temperature deviations, global, Arctic sea levels, Fargo temperatures, so on. Pulling in the Fargo temperatures, the first column is year. The average for the year is column 14. It goes January, February, March, all the way through. If I want to do a parabolic curve fit, my basis is year squared, year in 1. Solve for the constants, that's A, B, and C. That's my parabolic curve fit. Now what I can do is, how much has it changed over the last 80 years? In 1945, here's the temperature. That's this point right here on the red curve fit. In 2025, here's the curve fit. The difference is how much we've warmed up. 3.7 degrees Fahrenheit, assuming a parabolic curve fit. I want to know what will be the average temperature in the year 2050. Just make that the year. Here's my year squared, year in 1, times my constants, 48 degrees, 2100, 59 degrees. Now, again, this is kind of extrapolating out quite a bit. Also looking at the data, it's not quite clear, should I use a parabolic curve fit? Should I use a linear curve fit? You can use statistics to find out if the different terms are significant. We do that in 341 random processes. Using an f-test, I can show that the first term, the linear term, is significant. The parabolic term is somewhat suspect. There's not quite enough data to warrant a parabolic curve fit. But ignoring that, going with it, if I did assume a parabolic curve fit, that's what I'd get. The National Snow and Ice Data Center has been keeping track of how much ice is covering the Arctic since 1979. The blue curve is the minimum on a year-by-year basis. Given that data, come up with a linear curve fit. Same procedure. Pull in the data from the web. First column is year, second column is the ice level, the minimum. Do your basis is year and 1. Least squares curve fit, and there's A and B. Plot the two together, year versus the data in blue, year versus curve fit in red, and there's my linear curve fit. Now with that I can say, when does the function equal 0? That's the roots command. Based on a linear curve fit, the Arctic should be ice-free in about the year 2075 at the current trend. If I do a parabolic curve fit, just change the basis, year squared, year in 1. Here's your A, B, and C. Now it says the year 2064. Plot the two together, year versus data, year versus curve fit. That's a parabolic curve fit. A little bit of a bend in the line. Not much, but it is there. Again, for this data, whether you should be using a parabolic curve fit or a linear curve fit, we can analyze that when you take random processes. Actually, the data only warrants a linear curve fit the parabolic term isn't really justified given the amount of data that we have. But that's a different course. Finally, NASA Goddard has been recording global temperatures since 1880. That's 144 years of data. Find a least squares curve fit from the year 1970 to 2024. So there, I again just go to Bison Academy, pull in the data set, grab years 1970 to 2024, paste them into Matlab. First column is year, second column is the temperature deviation. Plot them, that's the blue line. To do a linear curve fit, make the basis year and 1, least squares curve fit, and you get, here's the slope, here's the offset. And it looks like the data matches up pretty well. A little bit of anomaly the last couple of years. From that data, I can extrapolate. What is the temperature going to be in the year 2050? So this says if I make the year 2050 my linear curve fit, ax plus b, it should be about 1.5 degrees warmer in 2050, 2.46 degrees warmer in 2100. I'll be plus 6 degrees in the year 2283. If I do a parabolic curve fit, change the basis to year squared, year and 1, same procedure. There's the parabolic curve fit, a little bit of a bend to it, a little bit better curve fit. When you take random processes, I can do an f-test to determine whether that term is warranted given the data. We'll leave that again for another course. With a parabolic curve fit, in 2050 I'll be 1.89 degrees, 4 degrees Celsius warmer in 2100, in 2134, 6 degrees Celsius warmer. That's problem 9. Problem 10 says, okay, so what does 10 degrees Celsius mean? Well, this actually isn't graded. It gets too political. But if you look at a journal article from Netherlands, they did global modeling studies to see what would happen. At 1 degree, you get heat waves that cause 10,000 deaths in France. And it's kind of Eurocentric. Crop production fails. That's already happened. That was the year 2021. 2 degrees. Oceans absorb less CO2, soil starts to release CO2, vacations to the Mediterranean or Gulf of Mexico simply become too hot. You get crop failures in Africa, Central America, mass migrations, coastal cities flood. 2053, that's coming up. 3 degrees Celsius, that's about 50 years from now. Crop failures in China, mass migration of more than 1 billion people, collapse of equatorial governments. 4 degrees Celsius, Spain, Mexico become deserts, mass migration to northern latitudes, rainforests burn up. That's the turn of the century, coming up. 6 degrees, basically end Permian-like conditions, really bad. That's part of the reason that climatologists are really worried about what they're seeing. It's not just one data set. CO2 levels, temperatures, ice levels, all the data is pointing to the same answer. We got a cliff coming. That's part of the reason we absolutely need to move away from fossil fuels. But there is hope. If you have to move away from fossil fuels, we need energy from some source. There is an option. There's renewables. There's solar, wind, geothermal, nuclear, hydro. That's our next lecture. And the good thing about that is not only can those save the planet, those provide jobs for electrical computer engineers like us. So that'll be coming up next week. But this is the solution to homework set number 4 for ECE 111.